Dew point versus relative humidity. You might have seen both of these indices on either your weather app or your home weather instruments. And what's the difference between the two of them? Because one is a lot more useful for many of us in our everyday applications than the other. So dew point is an absolute measure of the amount of water vapor in our atmosphere. It's the temperature that air needs to be cooled to for saturation to occur in order for dew to form on grass usually, or for water vapor to condense into water droplets or fog or something along those lines. And the dew point cannot be greater than our air temperature. So if we have an air temperature of 50 degrees, the dew point has to be lower than that. We can't have a dew point of 55, for example. On the other hand, relative humidity is the amount of moisture in the atmosphere compared to the air around it. At 100% relative humidity, the air cannot hold water vapor in the gas form and precipitation occurs. That water vapor condenses, you get precipitation or fog. So relative humidity is expressed in a percentage. Dew point is expressed as a temperature, similar to air temperature. So the dew point scale that you might have seen us use on air is this 5-point scale. Dry air, not a whole lot of moisture in the atmosphere, is a dew point less than 45 degrees. Pleasant air, not a whole lot of moisture in the air, still between 45 and 55 degree dew point. It's a bit humid when we have dew points between 55 and 65, muggy between 65 and 70, and downright oppressive, that air you can wear when dew points are more than 70 degrees. Remember, dew point, an absolute measure of the amount of moisture in the atmosphere. There's various ways we can measure dew point with these types of sensors, and you can also use a sling psychrometer, which is a little bit more of an old-fashioned technique that uses some cloth material to evaporate moisture to calculate that dew point. But the main point here is that dew point, absolute measure of the amount of moisture in the atmosphere. On the other hand, relative humidity, the formula for that is our condensation rate divided by our evaporation rate. And this evaporation rate depends on our temperature. That's why our relative humidity percentage will fluctuate throughout the day based on our air temperature. So let's have this little diagram here with our condensation rate compared to our evaporation rate. If we have a low relative humidity, the evaporation rate greatly exceeds that condensation rate. We have not much water vapor in the atmosphere, but it doesn't tell us a whole lot about how much water vapor we have exactly, because it depends on this temperature number. We'll get into how that plays out in a couple of seconds here, but the relative humidity and the temperature have an inverse relationship based on this equation. So when our temperature increases, our relative humidity decreases. Many times the relative humidity can be misleading. So let's say we have a temperature, air temperature of 30 degrees, a dew point of 30 degrees. That means our relative humidity is 100%. Our atmosphere is saturated. There's going to be fog that forms, or precipitation is relatively likely. Temperature of 80 degrees and a dew point of 60 degrees, our relative humidity is only 50%. But based on that dew point scale that I showed you a couple of minutes ago, you would say this dew point is very humid. We feel a lot of humidity in the atmosphere, but the relative humidity is only 50%. So it feels more humid in this case due to that high dew point, not because of our high relative humidity percentage. Relative humidity is dependent on the air temperature, as we've gone over, whereas the dew point usually stays constant. So another example here, air temperature 65 degrees, dew point 65 degrees, our relative humidity is 100%. We have saturation. Air temperature 80 degrees, dew point 65 degrees, we have a warmer day and our relative humidity is less at 60%. Whereas air temperature of 90 degrees, more summer-like weather, whereas a dew point stays the same at 65 degrees, that relative humidity is all the way down at 44%. So we didn't change the dew point at all in either of these three examples, but our relative humidity kept dropping as we increased our temperature. That's why you can kind of skew that relationship. And the relative humidity isn't useful a lot of times if you pull that up on your weather app. It's better to use that dew point to figure out how muggy or sticky it is outside. But what's an application for relative humidity? Fire weather forecasting. When the relative humidity is less than 20% Plus, we have strong winds and dry vegetation, meaning it hasn't rained a whole lot. The soils are very dry. That's fire danger. Fire weather warning or a red flag warning will usually be issued at that point. That's just different terms for that same type of warning that the National Weather Service issues. And this is helpful because our relative humidity is a measure of how close that air is to saturation. A low relative humidity percentage means that fires will burn more vigorously since any available moisture will just evaporate. Whereas dew point, like we said, that scale that we show you a lot of times, very useful to determine how muggy it is outside, also factors into our heat index, and the dew point can tell us how low overnight temperatures will be because of the principle that dew point can't be greater than temperature. So if we have, let's say, a 10 p.m. dew point of 45 degrees and we're trying to forecast the overnight low temperature, with clear skies and calm winds, meaning that we can, there's good radiational cooling, our heat will escape out into space very efficiently, we can say our overnight low forecast will be in the mid-40s because that dew point cannot be greater than our temperature. Our temperature will get close to that dew point and it'll fall down into the mid-40s, but it can't get below that. So some useful applications of dew point, some useful applications of relative humidity as well, but you can see that dew point is a lot more useful, especially when determining how muggy it is outside.
So true, right, Jacob? Because again, dew point's everything in meteorology.
Yeah.
It's a better representation than relative humidity, but even so, today's not as bad. Not quite as bad.
I just know that I am happier when it's not muggy.
And I'm happier when it's summertime and the days are longer.
Yes.